What we're going to be talking about today is the iMachining module in SolidCAM, and just kind of one of the things you see here at the top of the screen. You know, even a fast sports car isn't worth a whole lot if you can't see where you're going, and that's kind of how we feel about this style of machining. If you can't figure out how to set the parameters to make this stuff happen, then it really doesn't do you a lot of good. And so that's kind of what this meeting is all about today. We're going to kind of walk you through what makes this tick, a little bit of the science behind it, and give you a good view of how this works. What you're seeing here on the screen now is our patented iMachining wizard, and what this basically does, and I'll walk you through it a little bit later when we get into the actual software, but this gives the user a very, very easy way to simply slide the slider up and go from very, very conservative to very aggressive cutting strategies without having to manage a whole bunch of parameters. Now, there's a lot of stuff going on in the background. We're looking at the machine, the horsepower, the spindle speed. We're looking at the material, the toughness, the tensile strength, several other factors. And we are also looking at functions of the tool, variables of the tool, what kind of material it is, carbide, high-speed carbide, you know, various things like that. So we take all of those and bring those into concert and make them work together for you by simply sliding the slider back and forth. So that's kind of what makes this really work the best. Now, the part we're going to be working on is this goggles core mold over here that you see on the left-hand side. We're going to start into that right away and watch it cut, and then we're going to come back and talk a little bit about it. But I want you to kind of keep an eye on these sloped surfaces here. I want you to watch what the system does when it comes back. It'll do this same style staircasing that you see here, and it manages that based on a user-identified scallop height. And so all in one toolpath, we're going to see some very, very quick functionality here. Now, I'm getting ready to fire this up, so if you would, you can go ahead and slide your screens over so that you can see inside the machine a little bit better. And we are ready to rock and roll. All right, a little quick disclaimer. This is our first run on this brand new machine, and I think this is going to be fun. So here we go. Rapids at full, and we're ready. All right, and what we're going to do is we're just going to go ahead and helix right down into the part. Now, this is already going down to a total of about 735 thousandths depth of cut. This is a 3-flute end mill. This is 1018 cold roll steel that you're looking at. And now we're going to ramp up to about 12,000 RPM and between 100 and 160 inches a minute to remove the rest of this material in this cavity. As you can see, the chip ejection is extremely dynamic coming out of here. We're just using air blast. You can also hear the sound of the cut. A very, very clean sounding cut, a little bit different than what we're used to hearing in a machine. But as you can see, moving material very, very quickly. Now, our current spindle load is registering somewhere between 20 and 30%. So we're not really seeing a lot of load on the tool either. Very, very powerful situation going on here. You also notice that the tool is not coming up out of the pocket when it repositions for these cut moves. Now, the first thing you saw it do was what we call a spiral morph, and we'll talk about that a little bit later. But keep that in mind, that first series where it was just continuously running, that's what we call a spiral morph. And the toolpath actually changes shape from one shape to another within a range of cutting angle, allowing us to keep the tool in contact more and do less repositioning. The mode you're seeing right now is what we call a D-slot trochoidal or parallel passes. And of course the tool has to reposition each time that it makes this cut. Now, I'll show you when we get into the science here a little bit about how that works and what we do with that. But each of those reposition moves, we're also lifting the tool, in this case about 3/1000ths of an inch, off of the floor to make sure we're not dragging it. Now, we also support coming in from the outside and managing the outside of this core cavity or a mold cavity here, and remove the material out here very quickly as well. And again, you're never going to see this tool over-engaged. So the system is always working it. And notice those reposition moves. Again, we don't necessarily have to come back up to the rapid clearance plane. We can do what we call a detour path and use a high-speed feed rate to take the tool back to where it needs to go without having to lift it, change into rapid mode, change back into G1 mode, and so on. And that may not seem like a lot when you talk about this. You know, the machine has to come to a complete stop in order to switch from G1 to G0. And it requires a little bit of time. Doesn't seem like much until you start putting in, you know, several hundred or even a couple of thousand reposition moves on a large file. All of a sudden that hesitation time going from G1 to G0, G0 back to G1, well, that can eat up a lot of cycle time. Okay, now the other thing, go ahead.
Yeah, no, just mentioning real quick, Ken, the nice part about this too is I like how it regionalizes those cuts. So it's never, you know, it's not jumping up and down and creating all these rapid moves back and forth, and you know, it makes sure that it stays in its particular region until it moves on to the next.
Right, absolutely, absolutely. And that's done on purpose. We actually have spent quite a bit of time on our algorithm to figure out how to keep it in those areas as much as possible. Now, you're beginning to see it starting to do some of the staircasing. Okay, notice how it's lifting up off the floor a little bit. You're starting to see a couple of ledges appear there. And what's going to happen, it's going to actually start, it's continuing to rough, but it's also creating that semi-finished condition as it's doing this. Okay. Now I've got the staircases set pretty coarse today. I'm at about 65 thousandths of an inch, and so you can, that way it's a little easier for you to see them. But you can see what the tool is doing. It's regionalized itself very, very effectively. Now it does do a little bit of picking here and there around it for the express purpose of getting everything into the user-defined maximum scallop height. So once this is done with this roughing operation, you're not going to see anywhere on this model that's going to exceed that scallop height. That means your finishing tool is going to have a very, very consistent load and unload as it's cutting the finished tool paths that we're going to do in a few minutes. Now this also is a 7-degree slope wall on the outside here. And so as we come up in Z, we're going to have to take off some lateral stock as well in those areas. And again, as Brendan mentioned a moment ago, you can see how the system tries to regionalize as much as it can, kind of work in an area and then go work somewhere else. So it's not just jumping back and forth across the part. We try to optimize that repositioning functionality for you as much as we possibly can. Again, notice how dynamic that chip ejection is.
Yeah, Ken, this is unrelated to the presentation. We're getting several people saying that they can't see the live feed.
Oh, really?
Yeah. Trying to think here. I've got...
Is anybody seeing it?
I think we have a couple of people... Okay, we had one person go out and come back in.
I can see it again.
Okay, yeah. For those of you who are not seeing, for those of you who are not seeing the live feed, what I would suggest to do, the people that have, some people have logged out and logged back into the presentation. So that's what I would suggest.
Well, that's a little disappointing.
Yeah.
All right, now, let me explain for those of you who are seeing this what we're doing here. This is actually a 5-axis machine. And so what we're doing here, because we're cutting the floor, trying to put a little bit of a finish on there, I've actually tilted this over into a 5-axis toolpath so that we can keep the cutting point up on the side of the ball. Now, we're going to let this go ahead and continue finishing. It's got a little bit of work to do. And while it's doing that, let's go ahead and shift back, slide your screen back over. You can kind of leave that as a small picture because we'll want to kind of keep an eye on it. It's kind of interesting to watch it move through there and everything. But I want to get into the PowerPoint and take you through the science of the cutting angle. Now, is everybody seeing the PowerPoint? Or we have any issues with that?
It appears, Ken, that everybody can see the PowerPoint. We're just having some issues with the live feed. I don't know. I can see it perfectly fine on my end. I think, again, what I would suggest people to do is if they can't see the live feed, I would log out and come back into the meeting. That seems to be fixing the problem. I don't know why it's doing that.
Oh, boy. Okay.
So we'll, Ken, just continue on, and we'll get this straightened away here.
Okay. Interesting. Okay. All right. Well, let's go ahead and talk about the science of what we just didn't see.
Well, some people saw it and some people didn't. So
okay.
When they log out and come back in, they'll be able to see the live feed, and we can discuss it from there.
Well, we get everybody back into, and it looks like as I was scrolling through the questions, it looked like there was quite a few people that couldn't see. So
yep.
If we've got a little extra time at the end of this, maybe we can throw another piece up in there and run that roughing again so they can see it. Sorry about that, guys. I don't know what happened with the technology there. We tested it this morning, and it looked like it was broadcasting just fine.
Yeah, Ken, I don't think it's a part of the broadcast. I think it's a go-to-meeting thing because the only time we ever see this problem is when people are running Macs or iPads. So
yeah, normally that's all we've ever seen. So anyway, all right, getting into the science of the cutting angle. What we're talking about here today is how the tool is engaged in the material and how we control that, and what makes this unique and different from anything else that you've seen out there on the market. Now, I'm going to try to bring up this video. One of the questions that always comes up, are we really actually cutting metal? And the answer to that is no. I'm hoping you can see this video. Brendan, are you able to see it?
Oh yeah, yep, perfectly
okay.
fine,
Good.
No problem.
All right, this is actually a video, very, very zoomed in, very magnified view here of a 35-degree lathe insert passing through 1018 cold roll steel, same stuff we're cutting today. And as you can see, this is not really cutting. This is really more like chiseling is what's going on. This is about a 3 to 4 thousandths chip thickness here. But what I want you to notice is underneath here, you can kind of see the material bend out of the way and come back in. And that's a process known as elastic deformation. That's the ability of the material to be deformed from its natural state, but to spring back, essentially. What's going on up here on this upper line is obviously not elastic deformation. This is what's called plastic deformation. And this is really a disheveling or a chiseling away of the material. You're actually breaking the molecular bond in the material substrate. So I want you to kind of keep that in mind as we begin going through this and talking about the various different physics aspects of what you're seeing. Now, cutting edge velocity is extremely important. One of the things that we have noticed over the time is that as the cutting edge velocity goes up, the energy necessary to cut comes down. And I want to kind of illustrate that by talking a little bit about a sharp knife on a tomato. Even though we're not really cutting here, the same principle sort of applies. If you take a sharp knife, put it on a tomato, and just push it straight down, you will cut through the tomato, but you'll also squish that tomato as it goes down. If you take that same sharp knife and you drag it very fast across the top of the tomato, the knife will virtually fall through the tomato without any energy whatsoever. And through that, we can kind of see an illustration of what I'm talking about here, where as the cutting edge velocity goes up, the latent energy of plastic deformation comes down. Now, it's not a direct inverse linear proportion or anything like that. We really don't know mathematically exactly what it is, and I'm sure it's different for different materials. But what we've seen over practical testing on this is that we can watch the spindle load meter, and as we increase the spindle velocity for the same chip thickness of cut, we can see the spindle load come down all the time. and it just really works well like that. Now, one of the things that we want to talk about also is the stability of the pressure vector. Now, when I'm talking about the pressure vector, and I hope it's not getting too loud here in the background, we're getting into that fillet, and so it gets a little noisy right there.
Yeah, it's perfectly fine, Ken. No problem.
Okay, good deal. This pressure vector here, if the rotational velocity of the flute is in a good alignment with the forward velocity of the tool, and you're cutting over here on the climb side all the time, then the pressure vector will look something like what you see here. Now, this tool is designed based on the way they've cut the flutes to take that pressure. The pressure is underneath here on the concave side. We've got this convex curve out here on the outside of the tool that's designed to give us clearance from the part, but it's also designed to redirect that energy, that pressure vector, back into the core diameter of the tool. The concave curve in here inside the flute cavity is designed to curl the chip, take it beyond its creep rupture point, and break it, cause it to break off and therefore eject dynamically out of the cut, as you saw. If you were able to see the video, you saw what we were doing in there. Now, when all that's in alignment, we have a good situation. However, in a traditional style of toolpath, you can see that the toolpath motion is basically just an offset of the outer shape. And that creates what we call these compression zones, all these little sharp changes in direction where the tool becomes fully engaged in the cut. And it actually turns into a full slot width cutting mode. Now, there are several things that are bad about that style of function. One of them, the most important one, being that on the left-hand side of the cut, we're in a chip thickening condition. The right-hand side of the cut over here, you're seeing obviously, is in a chip thinning condition. Well, there's a lot of things that happen over here on the left-hand side when it's in a chip thickening condition. One of the worst things is that at the moment that the flute engages the cut, the pressure vector is almost directly opposed to the direction that the tool is traveling. And this is what creates this hard linear force against the tool, a bending force against the tool that has, over the years, limited us to being able to only cut anywhere from 1/2 times the tool diameter to 1 times the tool diameter in depth of cut before those forces get so much that we wind up breaking the tool. Obviously, also, as the flute advances up here to the 90-degree quadrant, you can see that pressure vector becomes perpendicular to the direction that the tool is traveling, and that linear force is what has created the need for a flex pass all these years. Okay? Now, we still do some flex pass cutting because it just helps us to dial everything in, but it's not near as dramatic cutting with iMachining as it is when you see it cutting in a full slot mode, because this right here is the absolute thickest point of the chip. And of course, as the chip is thickening, the latent energy of plastic deformation is increasing. Okay? Now, another thing that happens is a creation of a function we call pressure vector oscillation. And that happens when the flute crosses the 90-degree quadrant, because for that moment in time that the flute is actually passing the 90-degree quadrant, the rotational or the effective rotational velocity of the flute as it relates in the equation to the forward velocity of the tool becomes 0 for just a moment in time. And yet you still have that forward velocity on the tool. So what happens is the pressure vector actually flips to the outside of the tool for just a moment. And that creates an oscillation in that pressure vector. It also creates a negative force on that flute in a direction that that flute is not designed to take pressure. Now, we see this in practical application when we begin to see the harmonic vibration, the chirping and chattering that we hear in the cut. That is that pressure vector flipping to the outside. What we've done in our system is we have tried to avoid that by not allowing the tool to go beyond 80 degrees. Now, why did we choose 80 degrees? Well, in practical application, what we found as we looked at all this was we found that that seemed to be the point where between 85 and 90 degrees, we began to see this dramatic increase in the harmonic vibration. And so we looked at the difference between 80 and 85. There's really not a lot going on there. So we backed it off to 80 degrees and limited it there, because now we have a very, very stable pressure vector. As you could hear when we were cutting, a very smooth and consistent sound on the cut. There was no rising and falling of the pitch. It just was the sound of the tool engaging the material. Now we also have a minimum 10-degree cut, because we don't want to get too thin or we'll wind up in a burnishing condition where basically the fluid essentially bounces off the material and we're really not taking a cut at that point. It's also extremely inefficient, and so it doesn't make a lot of sense. Let's go back and do a review real quick. Let's look at a typical traditional style pocket has a problem because all of these sharp corners are what we call those compression zones, and those are the areas where the tool is going to be overloaded. That has always limited our depth of cut. Over the years, we did a few things like tricoidal machining that allowed us to essentially orbit the tool into those compression zones to try to mitigate some of those negative forces. It doesn't really resolve them or eliminate them, but it did back them off just a little bit, if you know what I mean. Okay. Wasn't really the best thing we could do, but for the time, it was the only thing we knew to do. Now, what we've done with iMachining is we have actually changed the tool motion algorithm, how the tool is actually traveling in the cut. There's two different modes. We talked about them a little earlier. One of them is called D-slot tricoidal, and let's go ahead and follow a cut line here. If we follow this line through here, you'll see that as the tool reaches this side over here, it actually helixes off the material right here, does a very high-speed G1 repositioning move, helixes back down in and takes the next cut. So as you can see, it just continues to do that until it works its way down into this corner, and therefore there are no sharp corners. There is no overloading of the tool. We're always managing the cutting angle. Now, another thing that we do is what we call a morphing spiral. Now, a morphing spiral is designed to go from one shape to another shape and keep the tool in contact the entire time. This allows us to minimize or sometimes eliminate the repositioning moves, and what's happening when you're repositioning, you're cutting air. So that's really not an effective thing to do with the tool. Now, in order to support the spiral morph, sometimes we have to separate that region from the rest of the part. And so we'll use what we call a D-slot tricoidal channel, a separation channel, to break through here and clear this area so that we can outside-inside spiral without running into the stock over here. Now you also notice a little something weird going on right here. Well, the idea here is if we took this channel at this same width right here, all the way out this side, we would wind up leaving a thin wall standing here. Now, with very rigid materials, we might get away with that. Any material that is kind of capable of bending, there's a good chance, because of how deep we're cutting, of it pulling the top of that wall over into the tool, which would of course cause the tool to break. So the idea here is that if we use what we call thin wall thickness parameter, and if the system sees that this channel would violate that thin wall, then it just expands the channel and takes that out as we go so that we don't have to worry about that. We just come back and do this spiral after that. Well, you can see there's quite a difference between this toolpath and this toolpath, okay? We don't have any sharp corners over here. Now,
you know, Ken, one of the things that people oftentimes they might say is, well, you know, that looks like an awful lot of toolpath. Is that really the case there?
Well, there is a longer distance of toolpath over here on a single level. Now remember, this one over here, if we're cutting like an inch deep here, you might only be cutting 50 thousandths or maybe 100 thousandths depth of cut. And so you're going to have to repeat this pattern over and over and over and over again until you get down to the bottom. The other thing that happens is doing this pattern, because of these compression zones, you have to run the tool significantly slower than what we did today, okay? So with the iMachining method, even though this is a little bit longer distance traveled, it does it so much more effectively, and it does it one time or a couple times depending on how deep it actually is going, but we can cut much deeper. I've actually cut up to 5 times diameter depth of cut without any issue at all. So it winds up being a lot more effective, a lot more efficient.
Sure.
Now let's talk a little bit about morphing spirals, because a morphing spiral in and of itself is not necessarily always the best thing you can do. Let me explain that. If we had a long, narrow region that needed to be morph spiraled, we come in here and we separate this from the back wall. If we were to spiral this entire shape, because of the long walls, we would have to cut, in order to start from one and come up to a central collapse point, we would have to cut down these long walls at or very near the minimum cutting angle of the range specified. Going across the sides here, of course, the short sides, we would be at or very near the maximum cutting angle within the range specified, which would be extremely efficient. But cutting down these longs, which would wind up being most of the cut, would be very, very inefficient. So what we did was we looked at a way of analyzing the topology of the region that needs to be cut and coming up with a way of breaking it into more symmetric regions where we could keep the tool closer to or at the maximum cutting angle, and of course make a very, very efficient spiral morph. And to do that, we use the spiral efficiency separation channels to break those zones. Okay? So let's kind of walk through a typical cut. And by the way, you can see that finish. That was a 4-inch by 6-inch by 1-inch block of steel, and we cut to a total depth of 750, and our cycle time on that, believe it or not, is right at 24 minutes. Okay? And that's with finishing, and I'll show you that part in just a few minutes so you can kind of see the surface finish that we achieved in that time frame. But let's go ahead and continue talking about this and kind of give you an idea how this works. Let's walk through a traditional or a typical style cut with iMachining. If it is possible, the first thing and the preferred thing we're going to do is a spiral morph. We're going to deal with the islands that we have to deal with, you know, whatever comes up in the topology of the model. If it's possible, though, we're going to switch back to spiral morphing wherever we can, because of course that keeps the tool in contact. You're not repositioning the tool. You know, obviously we got to deal with what we got to deal with, but if it's possible, we're going to put it back into the spiral morph whenever we can, even if it's just for a short period of time, because we're going to gain that little bit of efficiency. Now, at some point in the transition here, you don't have a choice. You have to finish it with parallel offset cuts. One of the things that we do, though, that's a little bit different is because we're using a range of cutting angle from minimum to maximum, we can actually morph these final cuts, and you can see we're cutting really, really long final cuts. And then we optimize the repositioning move by using the detour moves that we discussed while it was cutting. Okay? Most of the time we can keep the tool down and move it at a very high feed rate, because during the actual calculation of the algorithm, each movement that the tool is calculated also updates the automatic stock boundary, and so we know all the time where all the safe zones are, where we can move that tool without running into anything. And so that makes those parallel passes much, much more efficient. Now, two of the other things that we do are what we call iRest and iFinish. iRest is, you know, typical rest machining kind of stuff, remaining stock removal. But basically that allows you to use a larger tool out here and then come in and get these areas with a smaller tool and clean those up without wasting a bunch of time out here cutting things that have already been cut. iFinish is an interesting situation because, believe it or not, even with only 10 thousandths of stock on this wall, if this model radius is very near the tool radius, we can still wind up over-engaging the tool when it comes through here. You guys have all seen that, the diagonal chatter lines that it creates through here and the chirping when the tool goes into a corner. That's because even though we're taking off a very, very thin pass there, if we're not careful, when you come into this, if the ratio of that model diameter or model radius to tool radius is very, very close, you will over-engage that tool. So with iFinishing, what we do is we analyze the entire model before we take that cut, and we go find those zones where that will happen, and we go ahead and pick those out with our D-slot trochoidal style and make sure that we don't violate the minimum angle, because we don't want to burnish the tool going through there either, because that would dull the tool. So it's a very interesting way of doing that. Now, one of the things that we want you to think about, today you got to see a very high performance machine, actually a very high performance for the cost. This machine is not terribly expensive, and we'll get into that a little bit. But we also want you to know that we're not machine dependent. SolidCAM as a company is machine neutral. We don't recommend one machine over another machine. We're tool neutral. We're, vices and so forth. We don't try to tell you what you should or shouldn't use. But we also want you to see that iMachining can take whatever you've got and make it perform at a whole nother level. So I want to talk a little bit about this video. Now, this is not a real impressive video. This is an old, and I do mean an old, TM1 or TM2, I forget, Haas tool room mill, open bed mill. It's only got a 4,500 RPM spindle. The machine can only move at about 50 inches a minute before it starts getting into hesitation. The acceleration deceleration is terrible on it, and it's also very loose. I mean, this thing has been used hard for a lot of years. And so our customer, this is one of our customers out in Colorado, they were trying to cut a pocket very similar to this shape out using a 3/8 inch end mill. And actually they had gone out and bought some pretty decent end mills. They had OSG Exocarb 3150s in there. Real nice 3-flute high helix end mill, good coating and everything. But he was still only able to get standard pocketing style. He was only able to get one pocket per tool. And because of the machine's inability to stay sturdy and everything, the best he was able to do was cut this at 50 thousandths depth of cut at 2,200 RPM and 18 inches a minute. Pretty standard for that type of machine. So this pocket took 2 hours and 26 minutes to cut, and it burned up the tool by the time he was down to the bottom. What he was winding up having to do is he'd cut the pocket, the rough out, and then he'd change to a new tool, finish the wall, and then he'd use that new tool that just did finishing to go cut the next pocket. And of course, by the time it got to the bottom of the pocket, the tool was gone again. The 50 thousandths at the bottom of the tool was just toast. Well, as you'll notice here, I'm cutting it a full 1 inch depth of cut. Okay, same tool, same machine. Now you'll notice, you can kind of see the machine starting to hesitate. I'm actually using everything the machine's got. I'm running at 4,500 RPM instead of 22. And I'm running right at 50 inches a minute. In fact, I'm actually pushing it in some of the thin areas a little bit beyond that, and that's why it's starting to hesitate a little bit. So instead of watching this whole thing, let's go ahead and move it forward a little bit. You can kind of see, look at the color of the chips here. Really nice and gold, okay? And we're doing a lot of carving. Let's go ahead and take it up here further. And you'll notice still really nice, clean chips coming off of this, cutting at full depth. Again, not a very impressive video because it's not running super fast like we did today. But as we get up here to this end of it, let me go ahead and back it up just a little bit more. You'll notice right about here somewhere, we're getting, look at the color of the chip still. Really nice straw color. And there we are pulling off of this at 7 minutes and 25 seconds. So we had 2 hours, 26 minutes over here and wasted the tool. We had 7 minutes, 26 seconds here, and the tool's still in good shape. Now, we pulled this tool out, looked at it under a 3X loop. You couldn't tell it had been used. I mean, I would have challenged anybody to tell me that wasn't a brand new tool. Blew it off, wiped it down. There was no scuffing on the coating. There was nothing. Okay, so we put the tool back in. We ran 3 more pockets on this bar. And at the end of the 4th pocket, we pulled that tool out, looked at it again under the loop, and you could just barely see a little bit of scuffing of the coating on the tool. There was no microchipping of the cutting edge. The cutting edge was still razor sharp. There was no burning of the tips down at the sharp or chamfered tips of the tool. Everything looked really good. How many parts, how many pockets could I have cut with that tool at this rate? I don't know for sure. I suspect probably 10, 12, because at the end of the 4th one, the chips were still this beautiful straw color. The tool was still dead cold when it came out of the cut. We'd lift the tool up out of the cut, you could grab it immediately, and it was barely warm. Okay, we were not working that tool at all. So from that, I want you to kind of understand that we're going to take whatever equipment you have with iMachining and make it run significantly more efficient. Okay?
Yeah, Ken, and if I can add to that as well, really what we're trying to convey here is that we want you to be, iMachining will allow you to be successful with what you already have. You don't have to go out and buy a brand new machine like you saw on our live presentation. If you have one of those, that's all well and good, and iMachining will take that machine and make it sing. But it will also take your older equipment and make it much more productive than it ever could have been, just simply based on the iMachining algorithm. So again, what you're increasing here is you're decreasing your cycle times, you're increasing tool life, and you're decreasing the amount of wear and tear on either your brand new machine or that old machine that's been pumping out parts for 25, 30 years. So again, you don't have to go out and make some huge capital investment in order to make these machines work. iMachining will make that machine work for you.
Now, I do want to step in and say that the newer machine, the faster production, everything is going to gain you that much more. Okay.
Oh, sure.
So it is obvious that there's a certain time where you're going to want to do some capital investment. But now I want you to take a look here. I'm kind of sprinkling some of the chips in here so you can sort of look at them, and I'll pick a few of them up in my hand here. I want you to notice the consistency in those chips, okay? We were removing material very, very aggressively and just tearing it up, and yet the chip thickness is identical throughout the entire set of chips. And the reason that is because as we range the angle from minimum to maximum, we also range the feed rate so that we maintain the same chip thickness at the cutting angle, regardless of whether it's minimum angle or maximum angle. And so you see an extremely consistent load on your tool, and the chip thickness generates the same amount of heat all the time. So it makes that very, very functional. Now, I also want to kind of pop this out here a little bit and show you a little bit of the tricks that we did here. You'll notice as I roll this over, now I'm going to have to see where we are here. Sorry, I have to kind of step around to the side to figure out where the camera is looking. But as you can see, yeah, let me go back over here and let's roll it the other way and come back out so you can kind of see that angle down there. Whoops, too far.
Yep, there you go, Ken. That looks good.
Okay, and then let's go ahead and bring it down just a little bit more. As you can see, really, really nice clean surface finish on this, because in the 5-axis we're able to tilt it over for cutting this floor and really get the ball of the tool doing the work instead of working right off the tip here. Now, just doing kind of a coarse test here of what that is. That's well within 20 to 30 RA. That's a real decent surface finish on there. Up on these walls here, we're probably looking at, I would say it's 18 to 24 in that range. So here we finished this thing, roughed it and finished it in 24 minutes in steel, and yet we're still getting really nice surface finishes. Okay. So I want to do just a little bit of a shout out to our partners. Like I said, we are machine neutral, but Applied Machine Solutions Incorporated here in Ball Ground, Georgia, has been kind enough to allow us to use their machines to do these presentations, and we're really grateful to them for that. It does help us, and it also helps us in many ways. We're cutting on the machine all the time, so it helps us improve our software on a regular basis. But just even if you're not looking for a machine, I would recommend, if you need anything in the industry, whether it's coolants, work holding, tool holding, advice, whatever, Skip's a great guy to check in with. He's been in this industry for 30 plus years. He's got lots and lots of contacts. If there's anything you need in the CNC machining industry, I would be willing to bet you Skip's got some form of a contact for somebody that could help you out. So you might want to capture some of this information and give him a call. He is a Herco distributor here in the southeast, not all across the nation, but he also sells a bunch of other stuff, YG1 tools. The tool we were using today was a YG1, the ball cutters from GW Schultz. He actually distributes both of those. And so, you know, give them a shot if you need something. What I would say is the machine we cut on today is a VMX30U HSI. It is a Herco. And I would say to stay within that machine neutrality, the best I could say is if you are in the market for a new machine, I would definitely put one of these on your search criteria. Take a look at them, do a price comparison with a performance comparison. They're pretty darn nice machines, okay? There's a lot of good machines out there, but I'm going to tell you as a personal opinion, these are definitely one I would look at. When it comes to tools, again, we're tool neutral. We use GW Schultz, Mitke, YG. I use several different tools when we're doing these things. We do a lot of stuff with AccuPro, you know, just to show straight out of the MSC catalog. Here you go. It's not the tool that's doing the work; it's our software. Same thing with work holding. You know, we got a Tool X holder vise in there today. We had Jergens in there last time. Where I do bring up a little bit more of what I would call a less neutral opinion is when it comes to tool holding. Now, for those of you that got to see the cut today, I was cutting very, very aggressively. If you're going to do that, you need to hold on to that tool. I like this RegoFix Power Grip system. I have really seen it perform very, very well. It's very on-center. The run-out spec on it is fantastic. Because this is a hydraulic press in here instead of a heat shrink, the tool never goes into plastic deformation. It always stays in within the elasticity of this material, so you get a constant gripping force year after year after year, okay? With the heat shrink tools that do a real good job of gripping, the problem with those is the thermal cycling on them tends to put them into plastic deformation after X amount of cycles, okay? So a year down the line, it's worthless. You got to throw it away and get a new one. That doesn't happen with these, and their quality is fantastic. Let me kind of take that a notch further and show you why I'm talking about that. Now, this is an extremely aggressive cut here. We're cutting on a 10 millimeter tool at 12,000 RPM and 350 inches a minute, okay, even faster than what I was cutting today. Notice the chip ejection is extremely dynamic. I want you to keep your eye on this corner right here as this begins to continue cutting around here. And we're at 800 thousandths depth of cut here, even a little bit deeper than what I was today. So you can see it's just tearing material off there. Now watch what happens. See that line up here? See that line get deeper? Again, watch this corner right here. Look what's happening here. This is actually, and this is a really good milling chuck. This is not a cheap tool holder. This is a good milling chuck, but because I'm so aggressive on this cut, it's actually pulling this tool out, and as it's coming in, you can kind of see the staircasing down. The tool's coming further and further and further out of the holder as we go along. That's not a good thing. You know, they tease me all the time about the surface finish I put on the vise on this. But anyway, going further into this, let's take a look at what the RegoFix does for you. Now, this is the same tool, same depth of cut, different part model, but this time I'm running 14,000 RPM and 512 inches a minute at the same cutting angles. So extremely more aggressive than what you just saw in that other one that was pulling the tool out, and yet the tool doesn't get pulled out of here. Okay? And you can see this is just really going to town. Okay, moving some material. In fact, I was actually testing this tool. This is a very special tool that we've designed, and one of our partners ground it up for us and let us do some testing so we could test the chip ejection on this. So I was kind of pushing this thing beyond what I thought it would do. I was actually laughing the whole time I was videotaping this because I did not expect the tool to survive. This is actually the second part I cut with this tool, and at this speed, and it just blew my mind that it did as well as it did. A little bit of sparks coming out of here because the machine couldn't accelerate as fast as it needed to in that tight area. So with the spindle speed remaining the same, the chip thickness got really thin, basically just flared off. Didn't hurt the tool, as you can see. Might have burnished it a little bit. We probably lost a little bit of tool life on it, but as you can still see, it's doing a very, very fast job of removing material. And I want you to kind of get a picture on this. about right there. This is 1 minute and 27 seconds to take all this material. This is a 5-inch long by 3-inch wide piece, and we were 800 thousandths depth of cut on this. So we took all of that material off of there in 1 minute 27 seconds. And actually, like I said, I probably could have cut another 2 parts out of this at that rate, and that tool probably would have survived that long. I don't think it would have gone too much further beyond that. But if you're going to get aggressive, you're going to need to do some good, strong tool holding. Okay, if you're just going to go along, cutting at the standard rates and getting, some significant improvement on your cycle time, but you're not going to get crazy aggressive, you can use a good ER collet as long as it's nice and clean and you clamp it down good and tight. You can get away with that. But if you start to get, a little more aggressive, start to really push the feeds up and the angles of cut, especially the angle of cut. If you start getting up around that 50, 60 degrees angle in steel, you're going to start seeing the duration of time that flute is engaged is going to cause it to have more downforce on it. And it also has to do with the angle of the helix. This is a 50-degree angle on this tool, and so it's a really aggressive tool.
Ken, to add to that too, in looking at that video, I mean, it's every time you show that video, it's just incredible. I just get such a gas out of watching that. It's just
it's crazy, isn't it?
Yeah, it really is, and it just goes to show the power of the iMachining algorithm. And if you put all the right ingredients together, the tooling, the fixturing, much like Ken was saying, when everything is clicking on all 8 cylinders, man, I'll tell you, if material removal is what you do, it really doesn't get any better than that. So we'd also encourage you to go on YouTube and just do a simple search for iMachining, and you'll see tons of videos up there. In fact, a lot of those videos are customer posted videos, so you might want to just, yeah, we're going to throw out the disclaimer, the language disclaimer, because
yeah, no doubt. There's a lot of language in some of them.
A lot of those guys were, they're so impressed by it. You hear some pretty colorful language, and it's just amazing, some of these videos that are posted. So, obviously we'd encourage you to do that. Also, feel free to take a look at our website. We just have an absolute ton of information. Just go to www.solidcam.com, and you will see that we have just an absolute ton of material there. We have getting started videos, we have iMachining videos, we have getting started videos. We also have what's called our SolidCAM professor, which it's actually a true statement. We have a tenured professor who has actually helped design and develop iMachining, and also he does a lot of our training videos. So there's just an absolute wealth of information there. Please feel free to stop by and take a look at that. The other thing I just want to mention real quickly, Ken, is if people want to see a little bit more of this, if you have further interest in it, feel free to give us a call. Either talk to some of our area representatives or even our technical support staff. They'd be more than happy to take a call and sit down and talk with you about the product. So we definitely
absolutely
invite you to make a call here, and we'd be happy to talk to you.
You bet. All right, so at this point, I think we need to jump into the software itself for a moment. We're done with the PowerPoint here, so let me go ahead and exit out of that. Now, this is the part that you guys saw cut today, so I just kind of want to take you through the software just briefly. This is not going to be a full demo of our software, but just I want you to see what's going on with the iMachining toolpath. For those of you who are not familiar with SolidCAM, we do run directly inside SolidWorks, and we also have an InventorCAM product that runs directly inside Inventor. That allows us to take advantage of the solid associativity, which is very powerful. But each of our toolpaths, you're going to see this very same or very similar workflow. You're going to walk this tree on the left and fill out the data as you go down. Come down here, save and calculate. You can simulate here, even post G-code in here if you want to for a single operation. But basically, the geometry selection is as simple as picking the model, okay, in this case. Pick a tool. As you can see, I've got a 375, 3/8" tool selected. Set your levels. We're cutting a full -750. And then basically drive the wizard. Where do you want this to go, aggressive-wise? So if we pull it down here to 1, you'll see I'm only looking at 2,500 RPM, 19 inches a minute, and a step over of 34 thousandths to 12 thousandths. But as we start getting more and more aggressive, you can see those numbers really start to ramp up till we get up here to level 8 where we cut today at 12,223 inches or RPM at 153 inches a minute at max angle. As the angle goes down, this actually increases, and we could see feed rates of upwards of 200 inches a minute when we get down towards that 30, 40 degrees, or 30, 35 degrees cutting angle. So fairly aggressive cut, okay? There's a lot going on here. You can override the wizard when you want to, but basically understand that what's cool about the wizard, it controls all of that for you by simply knowing what's going on in the material, what's going on with the tool, what's going on with your machine. If you set those factors correctly in your post-processor and in your material definition and your tool definition, then this wizard just takes care of business for you, okay? Now, once you get to that point where you want to start doing some of what you saw me do today, we can help you modify the databases that are installed with the system so that you can make them a little bit more aggressive. But we also have a turbo mode in here. What most of our customers are doing is they're using the installed databases and they're running them up to level 8 or so. They start out down here around level 3, level 4, and those numbers tend to sound a little bit crazy for some people, but they cut really smooth on the machine. And so they'll all right, well, let's take it up a notch and cut it again. Man, it still looks good. Let's take it up another notch. Most of them are winding up about here with the default installed databases and discovering that, hey, I can still go faster. And so we put in this turbo mode in here where you can kick that turbo mode on and it'll pump it up even more for you. Now, we do have some of our customers that have done that and have gotten all the way back up to level 8 turbo and decided they still wanted to push it a little bit more. That's when we start working with them the database, show you how to modify the database and make it work a little bit more aggressively. Okay, so that shows it. Again, you can see here in the toolpath, we're cutting at full depth. This one cut all the way down. This one comes in, cuts all the way down on the outside, and then starts staircasing up. Notice it came up here, cleared the staircases, cleared this top area, and then there's a little bit of picking around up here to clear areas of this tapered wall to make sure that it's inside that dimension that we established for it. And that's as easy as setting the technology page. I told it I wanted to do rest roughing. I wanted a 65 thousandths staircase within 10% tolerance, and I wanted to leave 12 thousandths on the wall and floor for finishing. Okay. Again, very, very easy to set up, and yet creates a dynamic and very, very powerful toolpath. So at this point, let's go ahead and open up to question and answers. Brendan, have you seen any questions in there other than the cannot see and stuff?
The only other question we had since then, Ken, was somebody was asking about, since iMachining is machine dependent, does it need post-processors like normal SolidCAM? And
yes.
I sent a private answer saying yes, but do you want to expand on that a little bit, Ken?
Sure, absolutely. What we have to do, each of the post-processors, I'll just kind of take you in here real quick, there's what we call a machine ID, virtual machine ID. And in this, we have to tell the system, basically what's the spindle speed on the machine, and on the axes of travel, what's the rapid rate, what's the maximum feed rate, things like that. And by doing that, by giving the post-processor that information about the machine, what horsepower it is and so forth, there is a machine definition that we put in for iMachining. Now, I don't know what happened there. Hang on a second. In that database, when we set up the machine database for iMachining, we're simply telling it, again, the same thing that you saw in the VMID. What's the max spindle speed? What's the maximum feed rate? Do I want to use those rates for, repositioning cuts? What kind of horsepower does it have? And what level do I want to start at? Okay. And once you've done that and assigned a material database, like here I've assigned the material database, I have actually overridden the defaults in this and taken control of this myself by establishing these numbers. most of the ones by default are going to come in with all the automatic checks on, and all you're going to need to do is tell it what the power is, or for the newer ones what the ultimate tensile strength is and what the machinability factor of the material is, and the wizard will handle all the rest of that for you. But when you decide you want to take control, again, very easy to do. You know, what do you want to force in for the values that the wizard's going to use? And so through education, through our training courses, we can teach you all about that and get everybody up and running very quickly. But post-processors in our system are very, very easy to do, actually. Most of the time we try to do a post-processor out of our library. There are some machines still that require an extra amount of effort, and so we do have to charge every once in a while, but that's a rare item that we charge for a post. So,
sure. Ken, one of the other questions here was how long has iMachining been available? iMachining's actually been out on the market now for, I believe it's
4 years?
4 years, yeah. But development time was quite a bit longer than that. So
yes.
Ken,
yeah, the actual development on it began in late 2007, I think, was when we got the first alpha
right
to play with, and back then it was called Spiral Rough. And so we've been playing with it for quite a while. It's done pretty good now.
Yeah, absolutely. And, you know, again, just to kind of take that a little bit further, the 4 years that iMachining has been out have really just been amazing. We've seen a lot of company growth just strictly based upon the iMachining algorithm alone. And it's really, you know, people are really starting to stand up and take notice and really realize that this is a very unique process. In fact, it's a patented process. A lot of times, you know, people might look at this and say, oh, you know, well, I've seen that before. I've seen that in, you know, volume mill or true mill or dynamic milling, adaptive clearing. I can assure you that it's not. It's quite different. Like I said before, it's a patented process, and only SolidCAM can offer this. So,
right.
It's truly a revolutionary product. I know people like to throw words around like epic and revolutionary and you know, all this amazing, you know, all these huge superlatives. And with this product, I can actually use those words. It's really quite extraordinary. Yep.
So. All right, so that's about all we have for you today. If you have any questions, we'll give you a few more minutes to type those in. Else, we'll be doing this again, I believe, on the 28th. We're going to do our next one. And any of you that missed the video or missed the camera portion of this today might want to try to log back in then if you want to. We ran a little bit long today, so I don't really think we have enough time left to go back in and recut another one. But we'll try to pick that up on the next one.
Absolutely.
Question came in about the recorded video. We did not record today's. We do have a recording that we can get you a link to from, I think that was back in early November last year, or might have been before that.
Yeah, I think it was, Ken. I think
like that. And
right,
so,
exactly. Yep. But it does cover all the material that we covered today, for sure.
Absolutely. So we can get you a link for that if you would. Just send us an email requesting it, and we'll fire that right off to you so you can walk through it. And again, we'll be doing this again on the 28th of this month.
Very good. Well, on behalf of Ken and myself, again, thank you so much for stopping by. We understand how busy everybody is. Appreciate you taking the time with us today. And okay. So we do have the emails that people that are requesting, so we're all set to go here. Again, I do thank you for your time today. We understand that you're busy, and so again, thank you so much, and we'll be talking to you soon.